it's great to be here because ACSIS is very close to my daily activity. So I've been working with Danny for a while as a postdoc on CIS modeling, and now doing more on the remote sensing side. So I think ACSIS is one of the, so I'm part of CPOM, I should say, as well. So it's part of the key activities of ACSIS to bring model and observation together. So this is exactly a talk about that. So I'm going to talk about Arctic CIS volume budget decomposition of the CryoSat-2 period. I hope Paul Holland is not in the room because I'm a bit behind in terms of producing. No, the results are there, but the paper is a bit behind. So, but I think you will find it interesting. So with David Schroeder and Danny, we did engineer Schroeder some CIS modeling and comparing that with satellite observations. So we have, whoops, okay. Oh, wow, okay, that's the classic one. Sorry. Yeah, I'm gonna stop touching this one because it's highly dangerous with big thumbs. Thank you.
Yeah, so you're back.
I'm going to use the.
Yeah.
So I'm going to use this and then go back. So we have 5 columns here. CPOM, we have a CPOM CIS thickness product, so you might be familiar with that. Then we compared this for the last, so 2000, the growth, this is April 2011, 12, 13, 14, 15, 16, from the AVI product, the German product, and one of the NASA products here. So you see they all capture, in terms of observation, satellite observation, similar things. They're all from CryoSat-2, of course. And these are the CPOM size model in, these are anomalies, by the way. In April, the one that is initialized with satellite observations in November. So it looks quite close to what, after the growth season, to the real observations, because it has been initialized with observations in November. And we have a very good configuration in Danny's group with a free running model. So it's a CI standalone model in this case, but it's been calibrated and the physics is good enough to, on its own, capture reasonably well interannual variability. Of course, the regional details are a bit different, but the interannual variability is here. This is actually much better than most GCMs will have still today because of their poor CIs, not poor anymore, but yeah, less accurate CIS physics in the model. So having said that, we're interested to use both the satellite and the model to inform each other in terms of how well can we capture the growth between November and April. The CIS is freezing, so we want to look at that. And again, these are CIS growth anomalies in the CPOM dataset, in the AVI dataset, and the NASA dataset for the last 7 years. And you see that when you look at the growth, there are differences even between processing chains. So NASA will have much less growth 1 year than our products in Germany and in the UK. So this is something we need to understand more on the satellite processing side. The model can help us understand which one of these is maybe more in accordance to physics, because the model follows physics in terms of growth. You can grow faster than what thermodynamics tells you, and in that sense, the model is informative. And that's what David Schroeder did in his paper earlier this year. So you see in blue, CIS model size initialized with the satellite data from CPOM. The light gray curves are and the black curves are the CIS total volume over this red region from the satellite dataset from CPOM and AVI and NASA in gray. And you see that we're doing a good job overall. The model, the CIS standalone model, is doing a good job in capturing the growth. It's important to initialize the model with satellite data, because if the default size configuration without what we learned from the satellite and the new processes that we included in order to adjust our model to the observations was the light blue line. And you see that the default setting can be quite different. And most models, including the Met Office, for example, will have this type of bias compared to observations. So this is to show that the other way is true as well. The satellite, to leading order, the satellite CIS thickness will inform and constrain the model to a large degree. This is very clear in CIS focus, and we discovered that in the last few years, that initializing your CIS models and your meteorological models for the CIS in terms of thickness is much more important than in terms of concentration. So this is a bit of an illustration of that. If you don't start at the right place, you're nowhere, no chance to finish in the right place at the end of the summer. Okay, so I'm going to skip that and go to the key of the talk. So Paul Holland, who's from here and might not be here, but developed this method a few years ago to decompose these changes in thickness that I've shown you and volume. So he published that in Nature with Ron Kwok about 7 years ago. And he did it for concentration budgets. So he showed that the change of concentration over the Antarctic sea ice is a resultant of advective terms, this divergence here, a thermodynamic growth term, and a resultant which is ridging and mostly ridging terms. And if you do that decomposition over time, you can see that the total change, the top left part, is attributed to an advective part. So half of this divergence can be decomposed in advection and divergence, and the resultant will be how much of the ice is freezing, assuming ridging is negligible, which is quite true in the Antarctic. So this is to explain a bit better. There are two to explain advection and divergence in a nutshell. You can gain volume in an area, in a grid cell of your system, by bringing, for a constant velocity field of the ice, you can gain ice by bringing thicker ice and losing thinner ice. On the other example, you can gain ice by bringing ice of the same thickness at a faster rate. This is very basic conservation concepts matter. What comes in equals what minus what comes out is what equals what is created, right? And nothing is created. So no, something is created by growth and melt. Ice can be created or destroyed. So these are the data sets we use: sea ice drift on the left, sea ice concentration in the middle, and sea ice thickness from CryoSat on the right. And the novelty here is we try to apply this to sea ice volume. The reason why it wasn't done before by Paul Holland and others in real observation is that the data set is quite, so first of all, not many people are familiar with the sea ice thickness data set, and the resolution and the processing involved is quite challenging. So we set out to do this. It was a project now more than 3 years ago that Paul suggested. It wasn't funded at the time, unfortunately, by NERC, just not, but so we're trying to do that anyway. And here I'm presenting the first result based on this volume budget for sea ice thickness combined with concentration. So on the top left, you see the first budgets from satellites. So intensification will tell you on average, for November, December, how much is the change of volume in each place of this map. So red means that the ice is growing like crazy in November in the autumn season where it's very cold and it starts for very thin, and we understand that. The two middle plots are advective and divergence term. The advective one is quite easy to understand, for example, in the Fram Strait, where you have gain of volume due to the fact that you bring at the same velocity, say, there's a clear outflow in the Fram Strait. So you bring thick ice and you export thinner ice because it's kind of melting at lower latitude. So the differential means that you gain volume as you go through the Fram Strait in terms of advection. The important thing to see is that the resultant is the thermodynamic plus, it's just in the case of volume, there is no ridging, there is ridging that takes place, but ridging does not modify the total volume. So it doesn't appear here. So all the last line is thermodynamic growth or melt. Because we focus on the growth season, these are all positive. So there's growth very much concentrated in autumn at the edges, and then we see maps of this growth here. These are excellent tools to analyze the models, to scrutinize how well the models perform in terms of this decomposition in dynamic versus thermodynamic terms. And nobody could do that before having sea ice thickness and combining them in that way with the dynamic of the sea ice drift. So if you compare with the models, we use the sea ice model that David and Danny are working on to compare this analysis. And also it's a very good tool because you know everything in the model to assess the quality of your budget. And if you compare the two for the same period, there are several features that are consistent. And you can try to start to scrutinize differences in the model. If you have too much growth, for example, here, this is suspicious. This is a region of very thick ice to start with. So you wouldn't expect necessarily to have a fast growth if you start with a thick ice because of the insulation that it produces. And yet you have it in the satellite data. So that might be a hint that maybe something is wrong in there. So you can have all the months like this and really scrutinize the models. And I'm thinking also of the general circulation models. I would be really interested to test this method on GCMs. Yeah. So I've done, so again, this is, you can flick through model and observation each month at a time. We don't expect this to be completely equal because the model is in many ways, it doesn't assimilate the model in Reading any data, so we are quite unconstrained. So it's already quite impressive to get the same picture. You can then do volumes and look at fluxes outside of the system. You can look at pan-Arctic volumes. So here we compare the model again with observations. I'm not, you know, no, I want to say one thing about this. If you know the amount of, if you scrutinize how much of the change of volume is due to thermodynamics, this is very important for oceanographers as well. So if you know for the entire Arctic how much of the ice has melted in the summer or grown in the winter, these are fluxes in the ocean of salty water or of fresh water. And we're talking about large volumes. So this hundreds of cubic kilometers of fresh water coming in and out of your ocean. This is something that oceanographers are very keen to get. And it hasn't been possible yet from observations from thickness. Just to show you that we made some assumptions in the interpolation of the sea ice thickness, because the sea ice thickness from CryoSat is a monthly product. And here the budget analysis is done at daily timescales. So we had to make the interpolation between months with this, what these black lines are showing. And we tested how accurate this interpolation is with the model. So we used, again, size to test which places, these 4 points, which places are indeed quite smoothly varying. And most places in the Arctic in terms of thickness doesn't go up into daily timescale because it takes time to grow, except places like the Fram Strait that have a lot of advection and export. So you can see this variability that is obviously the simple interpolation is a bit too simplistic here. So just to say why we care, we had the project submitted on a specific key region that I think has been behaving very strangely in the last few years, especially last year. So you had these two large polynya openings in winter and summer. So understanding the preconditioning of this polynya opening in Greenland is very important for many reasons, exchange between air, ocean, but also it's a really symptomatic example of the fact that we're shifting to a new regime in the Arctic, I believe. The last time you had systematic open polynyas and open water in that region was 6,000 to 8,000 years ago in the last installation maximum in the Arctic. So this is quite an important signature of potentially things to come, more frequent polynya opening, and assessing that dynamics with these tools can be possible. And just to finish, how can it be possible? It can be possible by improving a bit, because that was quite a high resolution map. So to scrutinizing a smaller region, you need better data. So how do we do that? We bring in, we merge Sentinel-3A, B, and CryoSat-2 data. So this is a slide by my student, Isabel Lawrence at UCL. On the left, you have merged product from CryoSat-2 and Sentinel-3. Sentinel-3 is an operational Copernicus satellite that is really a mirror of carbon copy of CryoSat-2. And having more satellites will give you a better resolution in your products. In the same way, we have now better sea ice drift resolution. So combining these two, we can really zoom in this region and understand the changes that happen in the Arctic and have a better picture of sub-synoptic timescales variability of the volume. So this is something that will be very interesting. So I'll stop here. Thank you very much.
Are there any questions? One or two questions. Yes. What's the accuracy of the thickness retrieval in regions where the ice is really jumbled?
So the footprint is 300 meters. There are swaths. It's a quite narrow swath in terms of altimetry. It was a big innovation of CryoSat. It's 300 meters by typically 700 meters footprint. You can learn things about the sub-footprint information. And then the pixel I was showing here is an aggregate, an average of a monthly timescale, about 50 kilometer grid cell of an average sea ice thickness.
Colin?
The linear North Agreement.
Yeah.
From any way of understanding what the mechanism is?
So that's what we try to do with this proposal, but the driver has been understood to be largely wind-driven. So there's an atmospheric clear forcing of that. There's a bit of debate. People have argued that the sea ice preconditioning or the thickness of it doesn't matter. I find it quite, by using model studies, I personally find it quite hard to believe. Yes, normal is a very, very thick ice and very unusually for it to be broken away from the surface. So my personal feeling is that the rheology and the mechanics of the ice do play a role, and I want to understand that better. The other influence is from the ocean as well. There are things that happen there. So it's a very exciting place to understand change.
I
Okay, yeah. Okay, thanks, Michel.